My name is Henri Tresca, and I swear to tell you everything I know about mechanics of materials. So, as my name suggests, I am proposing the Tresca failure criterion. It is also sometimes referred to as the maximum shear stress theory because I propose that materials fail when the maximum shear stress is achieved. I know you're sitting there probably saying that sounds great, but what proof do you even have for it? Well, I'll tell you what, I want to submit a couple videos into evidence. So, Honor, if we can cue the videos up onto the big screen. All right, so in this first video, we have a mild steel bar that's being subjected to tension. So we're pulling it apart. We can see here when we hit the yielding that we start to get these diagonal lines forming. They're what we refer to as Luder's bands. It's actually the mill scale of the steel flaking off of the bar. I want you to look at those lines, those bands. What direction are those bands in? I think we can clearly see that the bands are on a diagonal. Oh, we could approximate the degrees, maybe. I think it looks close to 45 degrees, something like that. But we can see that it's starting to rip, or failure is starting to have kind of this diagonal path. Let's go ahead and keep loading it. Now I skipped through the video a bit. And you can see how ductile the material was because now the crosshead that's pulling the bar at the top is now out of the screen. So we can see that this is a very ductile metal. All the mill scale has flaked off for the most part, and we're continuing to stretch. It looks like we're about to get to the maximum load. We see necking, and then it fails. Let's go back to that point of failure. That's the best I can do to stop it mid-failure. What do we notice about the failure line? I think the failure line is on an angle. It looks close to a 45-degree angle, maybe a little bit less, but we definitely see that it failed on some sort of angled surface. So that's what got me to thinking that maybe it's not the maximum normal stress that causes failure, but it's the maximum shear stress. It's not just for materials like steel that's very ductile. Let's go ahead and take a look at this for compression. So here we see a regular concrete cylinder compression test. And when it fails, we get this shattering, but you saw that the cylinder failed at an angle. We're going to go back and slow that down. So look, fracture in this case initiated on an angled plane, which again suggests that it doesn't just have to do with the normal stress. Something else is happening that's causing it to fail on an angle. All right, so I hope you're starting to believe me when I talk about the shear stress. When we talk about, I want you to recall in Moore's circle right, we can draw more circle for an element, and I want to draw more circle for just our standard tension test. So you can see here we have a regular tension specimen. We're going to pull on this, and I want you to draw more circle for this scenario. This is much like that ductile steel bar. We're going to draw more circle for that. I want you to see how and why we think the maximum shear stress causes this 45-degree angled failure. To categorically prove my theory of the maximum shear stress causing failure, I want you to consider the uniaxial tension specimen on the left-hand side of the screen. This tensile specimen subjected to a load P, or we can consider it subjected to a load sigma along the axis of the specimen. I want to plot more circle for this loading condition. I don't have any stress in the x direction, so sigma x will be 0. Sigma y is going to have some value sigma, and sigma z is also 0. So labeling, plotting my circle and putting my points in here, I see that I have the case of just principal stresses. And so I can label my principal stresses sigma 1, sigma 2, and sigma 3, where sigma 2 and sigma 3 are 0. I go ahead and draw my Mohr circle for three-dimensional states of stress. However, since sigma 2 and sigma 3 are 0, I only end up with one circle. Now, we saw from the video that failure occurred on this 45-degree plane. So let me sketch my x and y axis here along with the 45 degrees. I see that that is 45 degrees clockwise from my applied stress. So from sigma 1, I need to rotate 45 degrees on my circle. But remember, when we rotate on Mohr's circle, we have to rotate through 2 theta to get to the equivalent stresses. So rotating 2 theta, or 2 times 45 degrees, will bring me 90 degrees around the circle, and that in fact brings me to tau max. So the plane that is 45 degrees away clockwise from the y-axis is the plane on which we experience the maximum shear stress. I'll refer to this as tau max absolute. So this is the absolute maximum value of the shear stress. We can calculate tau max absolute by taking sigma 1 and subtracting sigma 3 and dividing by 2. So sigma 1 minus sigma 3 is the diameter of this circle. Divided by 2, we get the radius, and that is the value for tau max absolute. Now, in my failure criteria, I say that failure occurs when the max shear stress exceeds a critical value. So in our tension test, the critical value is when sigma 1 reaches the yield stress. So when sigma 1 equals the yield stress, that's when this tensile specimen fails, if we're considering yielding as our failure. When that point hits sigma 1 equals Fy, tau max absolute is then equal to Fy over 2. So in general, we say failure occurs whenever the max absolute shear stress exceeds or is greater than or equal to the value of Fy divided by 2. Now you're probably saying, well, Mr. Tresca, this works very well for this uniaxial tension test, but what happens when I have more than one stress applied to the element? Well, I want to consider now a case of biaxial stress when we have 2 stresses acting on the element. So again, I'm going to order my principal stresses where sigma 1 being greater than or equal to sigma 2, greater than or equal to sigma 3. And now I'm going to apply tension in sigma 1 and sigma 2, and they'll have different values. If I was to plot Mohr circle for 3D stress for this particular case, I would plot a circle that connects sigma 1 and sigma 2. Then I can't forget that sigma 3 equals 0, the out of plane direction. So then I would have to plot sigma 3, and then I would have to draw a circle that connects sigma 2 and sigma 3, and a circle that connects sigma 1 and sigma 3. In this particular case, it's important to note that the tau max absolute, the maximum absolute value of shear stress, occurs on this larger circle. the circle that connects sigma 1 and sigma 3. So if you have a case of biaxial stress where both sigma 1 and sigma 2 are tension, you can't just draw the Mohr circle for sigma 1 and sigma 2. You also have to consider sigma 3 equals 0 so that you can identify the maximum absolute shear stress. I'm going to consider a second case, case number 2, in which we have sigma 1 applied in tension in blue, and then sigma 3 will keep a 0, and then we'll have sigma 2 be in compression. So I now plot Mohr circle for this case, the case in blue, and I would connect sigma 1 and sigma 2, I would connect sigma 2 and sigma 3, and I would connect sigma 1 and sigma 3. So in this case, where we have biaxial stress and one is in tension and one is in compression, we see that the first Mohr circle that we connected sigma 1 with sigma 2, that was going to give us the absolute maximum shear stress, and it's less important that we draw the Mohr circles that connect sigma 2 and sigma 3 and sigma 1 and sigma 3. I just want to reiterate the importance when you're using Tresca's criterion to make sure that you're identifying tau max absolute from your Mohr circle considering all three principal stresses. All right, so I'm going to just write down some information about case 1 and case 2. Technically, we should reorder sigma 1, sigma 2, and sigma 3 for the case in blue so that sigma 2 is really 0 and sigma 3 is really the compression force, because it is a thing in engineering mechanics to always order the principal stresses so that sigma 1 is the highest algebraically, then sigma 2, then sigma 3. I will also leave here a note, just always use the radius of the largest circle when you're checking for tau max absolute. Finally, I want to consider something called the failure envelope. In a failure envelope, we're trying to find out what combinations in biaxial stress, in this case, what combinations of sigma 1 and sigma 2 would produce a safe design. So we know we can take sigma 1 all the way out to Fy if we have no other stresses on it. Likewise, we could take sigma 2 all the way up to Fy if there was no other principal stresses. If we look at the red circles above, we see that it doesn't really matter where sigma 2 is between sigma 3 and sigma 1. Because sigma 3 equals 0, tau max absolute always falls on the circle that connects sigma 1 and sigma 3. So we draw the failure envelope that when sigma 2 is positive, the failure looks like that red kind of upper red square. However, in the case in blue, when sigma 3 is increasing, we start to lose some of that capacity because tau max absolute falls on that circle that connects the two biaxial stresses. And so therefore, in quadrants 2 and 4, we have a 45-degree line. And then we can repeat the case in quadrant 3 for just compression, and you would see that green square that I sketched. In the case of biaxial stress, any combinations of sigma 1 and sigma 2 that fall within this envelope are considered safe combinations. So if you have a engineering system, some sort of part, and you're doing the stress analysis, and you have biaxial stress, and you can identify the two principal stresses, sigma 1 and sigma 2, then you can find any combinations of those, and as long as they fall within this hexagon, they would be considered safe. To this point, I hope I've convinced you that Tresca's criterion of checking if the maximum absolute shear stress exceeds a certain value is a rational way to approach engineering design.
Engineering students of the jury, I know the best way to convince you that Tresca's criterion will be applicable to engineering systems
and that is by solving an example problem. So right here we have an example problem. We've done all the analysis to get to the stresses acting at a particular point. In this case, we see we have the condition of plane stress. So we have stresses only acting in the XY plane. The stresses are shown, and the steel has a yield stress of 50 KSI, which would come from the uniaxial tension test. I want to use Tresca's criterion to determine if failure occurs, and then I want to include a factor of safety of 2.0, and then check using Tresca's criterion to see if failure occurs. So let's go ahead and solve this. Now remember, Tresca's criterion says that failure occurs when the absolute maximum shear stress reaches a critical value. So we need to determine the absolute maximum shear stress. And I think the easiest way is to use Moore's circle. So let's go ahead and plot Moore's circle for this particular case of stresses. So we come in and we can identify the stresses. This was step number 1. Draw the sketch of the element and then identify the stresses. So I see I have sigma x equals 16 KSI, sigma y equals negative 8 KSI because it's in compression. Tau xy, my shear stress, is going to be a negative 10 KSI. Because again, this is the positive x plane, but that's the negative y direction. So this is the case of negative shear stress based on our sign convention that we've been using in this class. I also want to be careful to also indicate that the stress on this plane pushing in and out of the board in the z direction is 0 because we have no information to say that it's anything but 0. So I want to also make sure we write down that sigma z equals 0 because that's important. We have to make sure that gets onto our Moore circle as well. So we now walk through our steps of Moore's circle. We set up a coordinate axis with tau positive downward. And I'll go ahead and give some units. Sigma positive to the right. Step 3, we plot our points. We plot a point at sigma x comma tau xy. So that's going to be 16, negative 10. So I come across 16. I'll make each block maybe 2. So 2, 4, 6, 8, 10, 12, 14, 16. So this will be 16 right here. And then negative 10 is going to be upward, so that's going to be 2, 4, 6, 8, 10. Right about there. So I'll plot that point. Let me get it in red here. This is the point 16, negative 10. I also need to plot sigma y minus tau xy, so that's going to be negative 8, positive 10. So I'm going to come over here to negative 8, 2, 4, 6, 8, positive 10, 2, 4, 6, 8, 10. 1, 2, right there. This is the point, negative 8, positive 10. And then I connect these two with a straight line. All right, I think that gets us started. Then we can find the center. So our center is right here. So it's going to be halfway between the two. I could add these two together and divide by 2. And I would see that my center is located at 4, 0. Let me see if I can even fit that in here. There we go. So I got the center of my circle. Now I can draw my circle. Not too bad. So I see my circle looks something like this. And I can identify now what this radius is. So the next step was to figure out what this radius is. My radius, see my height is 10. My distance here is 12. So the radius, r squared equals 10 squared plus 12 squared. That's going to be 244. So r is going to equal 15.62. All right, I'd like to be complete, so let's go ahead and identify some of our principal stresses. This would be our first principal stress. We have another principal stress over here, and then don't forget that sigma z is also a principal stress. So I also have to have a principal stress here at 0. Then I'll just algebraically number them sigma 1, sigma 2, sigma 3. I want to draw my Mohr circle in 3D, so I'm going to add my circles, my other circles between these two. So we can add a circle in here. We have another circle that connects 1 and 2. Like that, and we've now completed Mohr's circle. Now, for Tresca's criterion, we need to determine what the absolute maximum shear stress is. The absolute maximum shear stress, as it falls on this circle, is going to be on this blue circle below the center. And this should be the lowest point. So maybe my blue circle has got slight skew to it. This should be the bottom of my circle. I'm sure you guys did a better job of drawing that in your notes, especially if you pulled out your compass. I always encourage that. Or if you're using a digital thing, of course, the circles look perfect, right? All right, so this is our Mohr circle representation, and this is now my tau max absolute is what I call it. So the absolute max shear stress. What is the value of this? The value is going to be, in this case, the radius of the blue circle. And what is that radius? Well, that radius is what we calculated here. R, which was 15.62 KSI. Okay, so now we're ready to apply Tresca's failure criterion. All right, so we said that failure occurs when tau max absolute exceeds a critical value of Fy over 2. If you like to use the graphical representation, great. I think it's easy to see that this is the maximum absolute shear stress, 15.62. But other people like to have this as an equation in terms of the highest principal stress and the lowest principal stress. So we could also have got here by taking sigma 1 minus sigma 3 dividing it by 2. And just to show you that we can do that, let's go ahead and solve for sigma 1 and sigma 3. So we have sigma 1 is going to be the center plus the radius. So that was 4 plus 15.62. So that's 19.62 KSI. Sigma 2 is 0. Sigma 3 is the center minus the radius. 4 minus 15.62 gives us a negative 11.62 KSI. All right, so we can go ahead and plug that in. 19.62 minus 11.62 divided by 2. Over 2 has to be greater than or equal to. In this case, the yield stress was given to us as 50 KSI divided by 2. So this should give us tau max absolute, 15.62 KSI. We ask, is that greater than 25 KSI? So sometimes I like to put a little question mark here. Is this greater than this? No. So, no. Failure does not occur using Tresca's criterion. All right, hopefully that was pretty easy to see, easy to follow along. And so now we have a means of checking failure. So it's not enough that we can just come up with the stresses at a point. We need to check failure because ultimately as engineers, that's why we're here, to make sure things and systems, buildings, bridges, cars, turbines, dams, all of these things, that they stay safe. So we got to check failure. We also like to include factors of safety when we do this. So the most basic way to include a factor of safety is to modify the yield stress. So in part B, we're asked to use a factor of safety of 2. And so what we're going to do is we're going to apply that factor of safety directly to the yield stress. So for part B, we want to include a factor of safety. So now, I'll say failure, or maybe failure to meet design criteria when tau max absolute is greater than or equal to, and now I'm going to apply my factor of safety directly to my yield stress by dividing it. And we still have to include this 2 from the original formula. So now I have a formula that includes the factor of safety. So the math will remain the same. This will turn out to be 15.62 KSI. We ask, is that greater than or equal to? Now we have our 50 KSI divided by 2.0, because that was our factor of safety, divided by 2, because that's part of Tresca's criterion. So that's going to give us 25 divided by 2, that's going to give us 12.5. So is 15.62 greater than 12.5? Yes. So in this case, yes. I would say our design does not meet criteria with our factor of safety. Or you could say failure would occur, or failure to meet the design criteria. I just want to keep in mind, though, that when we apply a factor of safety, it's because we're trying to make sure that we really don't want it to fail. So I just want to be careful with using our terms of failure. It's more, in the case of a factor of safety, a failure to meet our design criteria of being safe whereas it might not actually result in physical failure, because without the factor of safety, Tresca predicts it doesn't fail, but remember we saw some variability in the data points, and so we want to be extra careful by including that factor of safety and making sure that we stay safe. Alright, so hopefully this problem was pretty simple to go through. Hopefully you enjoyed using Moore's circle once again to figure out the absolute maximum shear stress, and I look forward to hearing your decision on whether or not Tresca or von Mises's criterion is the best. Remember, Tresca. Thank you, ladies and gentlemen, for listening to my case for the maximum shear stress theory of failure, or Tresca's failure criterion. I hope you found that it was very easy to apply, very useful, and because of that evidence, that physical evidence we looked at, was very conclusive that my stress criterion will be applicable to your engineering systems. I now rest my case.